a lot to cover I think I have a lot to cover today, and I think the agenda is to actually first of all bring everyone to the same page, because I don't think key phrases has been very well explored topic um, like the other topics. For example, I see named entity extraction, question answering, summarization being very popular among the NLP researchers, but I think a lot of people have a lot of confusions in understanding what exactly is automatic identification of key phrases. So I wanted to bring everyone to the same page before I dive deeper into some of the latest work that we have done. So so I think after that I would like to cover one of the most latest work that we have done, which I'm really excited about, and this is about training a new language model which really understands rich representation of key phrases from text. And then I'll be talking about a work in progress, which is DLKP, which is a deep learning library for identifying key phrases. And this is something that I've been working on at this point. Okay, and would like to introduce it over here, and would like to have some volunteers who can help me to build this library. And then I think lastly, I have to briefly talk about AI at Moody's and what are the opportunities that we have at Moody's, which might excite some of you in the audience. So let's get started. So what is identifying key phrases all about? Okay, so if you look at this particular slide, here's an abstract of a paper, and then what essentially key phrase identification is all about is that you train a machine learning model which takes this paper as an input, or this abstract to be specific as an input, and actually gives or extracts or identifies most important phrases that can concisely describe this abstract or summarize this abstract. And it's a form of an extreme summarization. So as you can see over here, the machine learning model was able to actually extract a lot of interesting phrases from this abstract, which is document summarization, domain specific key phrase extraction, key phrase extraction, author assigned key phrases, naive Bayes, which kind of gives a very a solid understanding of what this paper might be about. It kind of makes you understand, okay, this paper might be about key phrase extraction, and the authors might have used naive Bayes as one of the modeling technique to identify key phrases. Now this is another example from a news article, and this is basically saying there are a lot of keywords, and if you look at these keywords, you kind of have an idea that this news article is probably about Muslim women and girls, and some kind of hate crimes committed against them probably in Canada. And so now if you look at the examples again and stare at it a little bit, okay, now you'd see all these key phrases that you see over here can be actually found in the actual text. And these key phrases are what we call extractive key phrases. And the process of identifying these key phrases from actual text is called key phrase extraction. Now, if you look at this example again, now there would be certain phrases like US, Islam, fashion, wheeling, girls, journalism, which you may not find in the actual input text. Now, these key phrases are often called abstractive key phrases or absent key phrases. And the process of identifying these phrases is known as key phrase generation. Now you must be, thinking about, abstractive and extractive summarization, because that's something very popular, and often you read about, the researchers working and reporting their results on, especially the model language models in that task. So key phrases, I think the analogy is pretty much the same. It works, but key phrases are not exactly summaries, but it kind of is an extreme form of summarization. Now, if you have actually noticed, the two examples, in one of them, the key phrases are referred to as key phrases, and the other one, it's referred as keywords. So before I proceed, I just wanted to, clear this confusion, because, I have faced this confusion many times while talking with, other researchers. What was the difference between key phrases and keywords? And I know, are there different? Are there different techniques to identify them? So essentially, they are not different, and they are pretty much the same. And basically, the words key phrases and keywords are synonymously used throughout the literature, and they are essentially important descriptors of the document content. And except that key phrases are more generic according to me, and I think key phrases represent single as well as multi-word phrases. So I tend to, prefer to use this word of key phrase rather than keywords. Now, what is key in these key phrases? So now all phrases cannot be key phrases, right? Let me tell you a secret. If you take some of the existing data sets today, which are useful for benchmarking key phrase extraction and generation, and keep it a secret. Okay, so you'll find like more than 68% or 70% of them are noun phrases. Okay, which is interesting. And this is something that I actually found out recently while I was actually, looking at some of these phrases um, and trying to understand them. So now, but then, you can say like all the a majority of the key phrases would be noun phrases, possibly, but it's not true the other way around. Okay, so
can you say what a noun phrase is specifically for non-linguists? Is it just a noun, or does it have a different meaning that I might not know?
Oh, so it's basically actually noun phrases are actually basically a sequence of nouns along with certain other phrases. I don't exactly remember exactly the definition of it, but basically, things like, named entities, any expressions which has nouns along with adjectives, a sequence of phrases. I think, noun phrases are pretty popular, like noun phrases, verb phrases, which kind of identified, the main nouns and actions, subject, actions, objects. So I think, yeah, I would not attempt a definition of a noun phrase, but yeah, it's something, that you can probably, look at later. So now, when it comes to the keyness properties, there are certain properties which, the work that I have referred to in the slide has identified, which kind of identifies any phrase as a key phrase. But this is not a well-defined, actually, set of properties. And there's no basically common consensus at this point, that what exactly a key phrase is. And it kind of, sometimes depends upon the context and, the perspective, and the reader. It might depend upon the reader who is reading the article or a document. It might depend upon the author who is actually authoring the document. So different people actually look at the same, content with a very different information seeking behavior. And to be very frank, the key phrases are often, sometimes, dependent upon that. But these are some of the properties, you can, look into. And I would like to specifically mention the property of exhaustivity and specificity, which kind of covers, most of the, most of the work that I see. So I think when it comes to exhaustivity, what essentially we want to do is that, given an input text, we'd like to actually cover, or we would like to extract all the phrases which represent all the major topics covered in that text. And when it comes to specificity, it's a little bit of an opposite, where we'd like to be very, very specific which kind of uniquely identifies, or would like to identify those phrases which are very unique to that particular document, and uniquely help us to uniquely identify that document. And think of TF-IDF measures. It's very it's kind of, you can draw an analogy like that. So apart from, these informational properties, there are other linguistic properties which, which kind of are important, because you don't want to see a phrase which does not make sense linguistically. So I think well-formedness and citationness actually is an important criteria. And then there are obviously domain-based properties, right? And I mean, the same key phrase can be, referred to in a very different way, and different domains have their own jargons. And so that is, and there are several domain-based properties which help you to identify key phrases which are very domain specific. So I think, this paper is a very good read. You guys can go ahead and read it later on. But now, why would we at all bother about key phrases? So I think there are several applications, and especially in industry, you know, there are like the key phrases really help in information retrieval systems, then understanding documents, indexing documents, even analyzing events. They're a part of, content-based recommender systems. They're all almost always, I find, they are a part of the text analytics and information extraction stack in any industrial setup. And I think digital libraries is one of the major field where, key phrases have been researched a lot. And I think most of the, major advancements that has happened in this area has been driven by some of the researchers who are working in the area of digital libraries. And then knowledge management, like ontology creation, term extraction. So I think there are many more applications to key phrases. So now, I'll quickly go over, the major, benchmark data sets and evaluation strategies for, key phrase extraction and generation. So if we look at the sources of these benchmark data sets, they mainly come from, three primary domains, like scientific documents, news documents, and web. And I think, we'll soon see, actually. So the majority of them are from scientific documents. And there's a reason, right? I mean, I think you've all guessed it by now. I think often we as researchers, when we publish papers and we submit papers to journals and conferences, we often are asked to actually give a set of phrases or key phrases or keywords which accurately describes, the work that we are submitting. So these are often called author assigned key phrases. And and since we have a huge amount of research papers with all these key phrases already assigned by the authors, I think they prove to they tend to be a very good candidate for benchmarking these algorithms. Now in news documents also, there are editors who often actually assign key phrases in news documents for various purposes, for indexing news documents, for categorizing news documents, and many other editorial needs. And so there are some data in news documents as well, but there's only very few data sets which are in the web domain. And actually there's a lot of need of data sets, and we'll look at it very soon. So when it comes to annotating this data, there are primary three ways. One is the author assigned, reader assigned, and professional indexer or editor assigned. And if you think a little bit, their perspectives are very different, right? And so author assigned key phrases are very popular, of course. But if you actually have to get it annotated by readers, okay, then you have to actually spend a lot of money in annotation process, and it's basically not that popular. Okay, but there are certain other platforms which allow you to do these annotations. For example, Stack Overflow and many other crowdsourced platforms, which asks you to assign some topical phrases, which actually helps you to identify these posts. So there are certain times, often posts are tagged, but it's very rare. And professional indexer or editor assigned, this is like very specific to news domain, and it's something not very common at all. So we'll see how today what type of benchmark data sets we have. Now, one of the key challenges in this key phrase domain is
All question.
uh,
Yeah. So I think the assigned is the one which is the easiest if done, like compared to I think a reader assigned, and it's more I think more better or something, like it is more abstractive also I feel than the reader assigned, I feel, because it's more likely if you are an author then you can think about phrases which maybe not written but might be relevant to the piece of document. Correct? Am I correct in this?
I'm exactly coming to that.
Okay.
Yeah. So basically, there are no annotation guidelines, to be very frank, and it's totally domain dependent. It's totally dependent upon the person who is assigning these key phrases, and it's very hard to actually come up with some standard guidelines. And as Vivek actually suggested, and was saying, author assigned key phrases are often subjective, and there's an intent bias, right? So you as an author would like to assign those phrases which can actually make your work more discoverable. So there is a kind of hidden bias to assign some phrases which are even more generic, abstractive, and exhaustive. So for example, if I am so suppose publishing a paper on Keyphrase extraction and I've used a deep learning method, I would tend to say like assign a lot of phrases which may be not related to exactly key phrase extraction, but I'd also include key phrase generation, identification of key phrases, deep learning, and whatnot. Okay, so that my work is more discoverable. So yeah, that is true, whatever Vivek was saying. And also reader assigned key phrases also have a lot of subjectivity. One of the key problems and challenges is that the readers are not often the expert in that area. And so, they tend to basically rely pretty much on what they are seeing. And so the key phrases tend to be extractive, more specific. And one of the greatest challenges is they have a very low agreement. So if you have a document and if you ask like 3 readers to assign key phrases to them, I think the agreement would be very low. And this has been already reported by multiple studies. And this is one of the key challenge, of course, to annotate data for key phrase extraction. And the indexer and editor assigned key phrases often um, are are of high quality, and but they also have a little bit of subjectivity, but they tend to be very controlled. So they generally come from a controlled vocabulary. So so basically our editorial team would have a controlled vocabulary or a thesaurus which they are going to use for probably assigning some key phrases to the news article they are actually going to publish. So these are like some of the various flavors of data annotation for key phrases, and some of the challenges associated with each of them. Now, there are multiple data sets available on the scientific domain, and this is the most popular domain in which you can easily get the benchmark data sets. But if you look carefully to it, most of them are basically author assigned. There are 1, 2, 3 data sets which also has reader assigned key phrases, but these data sets are extremely small. And the only huge data set is KP20K. And apart from that, there's OAGKX dataset, but they generally don't have any train dev test split. It's not very popular. So it's now becoming popular for doing or training language models, but then it's not really popular to report or benchmark your because it's very noisy. And but KP20K, on the other hand, is the only data set in the scientific domain, which is pretty big. Then when it comes to news and web, okay, so the situation is even more um, actually hard. I mean, in news, there's hardly like one, like, and two data sets which often is being used, KP Times and DUC 2001. And if you look at DUC 2001, it has only a small amount of handful of articles. And KP Times is the only data set which has a lot of news articles which are actually annotated by indexers or editors. But then, if I actually look into this data set, I think, I get a lot of noisy labels, and it's very hard to train a very good model on this data set, which is not something, so this is something that I would like to, probably explore in the very near future. And and then if you look at the web, there's only one corpus which kind of is a good, can be used as a very good benchmark corpus, which is from Microsoft, and it has a very good amount of articles, and this is a very high quality corpus. So they have a lot of annotations, and they did a lot of studies related to annotating key phrases, and this is something, a very good corpus to train your models on. And it's basically documents from web indexed by the big Bing search engine. So now, given this situation, I think there's a lot of need for actually data, because if you look at these supervised models that we train today for key phrase extraction and generation, if you train it in one particular domain, it's very hard to get good performance in other domains. And in real life, basically, you don't actually get scientific articles, because if you're working in Moody's Analytics, I don't think you'll be, extracting key phrases for scientific articles. And, so there's a need for data set for performing key phrase extraction in the wild. Okay. And that is something completely missing as of today. And there are also lack of large data sets on long documents, because most of the data sets that, if you have noticed before, this is the only large data sets, and it only consists of abstracts, and they don't contain the entire scientific document, which is like most of the time 20 pages or so. And it's often seen that not all the key phrases can be obtained from the abstracts. And there has been previously studies which has reported that. And there's hardly any language coverage. I mean, there's hardly any key phrase extraction or generation data set, beyond English. There's one or two, French and Portuguese. And I mean, I am not aware of any such. And also, like, the domain coverage is also very low. So most of them are in scientific domain. So I think these are some of the data needs. I'm sure, like, some of you are like researchers, and are very interested to curate data. So yeah, please help the key phrase community if you are interested. There's a lot to be done in this area. So given these data needs, we actually created a new corpus, okay, which is again in scientific domain. But then these are all long documents instead of abstracts. And what we did is that we took the KP20K corpus and OAGKX corpus, which has a lot of articles, and we mapped these corpus to S2ORC corpus, which has been actually made publicly available by Alan AI. And what S2ORC gives us is that the entire documents with all the metadata along with it, and all the all the pages of the documents. But on the other hand, KP20K and OAG gives us the key phrases. So basically we tried to actually find the same documents in the H2ORC corpus, and then we map these documents to the H2ORC corpus, and now we created a new corpus which we call as LDKP, and it's available in different sizes. So we have a small, medium, and large training data sets. Okay, so I know like a lot of us are students and might not have like all the resources to train, big models. So we decided to actually, release this corpus as small, medium, and large, and it has all the metadata along with it, which could be probably useful, in a future study of key phrase extraction and generation. And there have been previous studies which actually says that if you can actually use the citations information to generate and extract better key phrases. So this corpus is available publicly, and it has a very good coverage of domains, different kind of domains. And all of this is available publicly in Hugging Face Hub. Okay, and apart from the obviously LDKP corpus, there are other corpus that are the benchmark data sets. We have also made them available in Hugging Face Hub. So you can basically, just, pip install the datasets library, just name the corpus that you want to download and get it in your laptop. And so more on that actually.
I have a question. What is 3K and 10K LDKP?
Oh, okay. So this is basically, so we basically still go with the KP20K type of naming conventions. So if you look at this data set, so LDKP3K is the data set that was mapped to KP20K, and LDKP10K is the data set that was mapped to OAGKX. Now we couldn't find all the 20K. Okay, we couldn't map all the 20K papers which are available in KP20K. So this is just named based on the amount of documents that we have in the test data. That's it. So as I said, all these resources are available for publicly to use. Now let's look at the evaluation metrics. This is interesting actually. So this is a little bit different from what we are used to in other machine learning problems. So precision at K, recall at K, F1 and K, this is the most widely used metric in traditional key phrase methods. And I think this is something that a lot of us are familiar with. And precision recall and F1, this is a very popular key phrase metrics for key phrase extraction when we treat this particular problem as a sequence tagging problem. And then there are other two methods which are widely used in key phrase generation, which is precision recall and F1 at O and M. So let's quickly understand this. So precision recall and F1 at K is very easy. So you extract all these key phrases, you rank them, and you extract only the top K predicted key phrases based on which you just calculate the precision, recall, and F1. But now, F1 at an AM and O is something interesting. So consider a case that a document has like 7 gold phrases and a model predicts, suppose 10 phrases. So M basically denotes the number of predicted phrases and O basically denotes the number of ground truth phrases. And like 5 of them are correct. So precision at M would be, precision at 10 because 10 is the number of, phrases that your model predicted. But precision at O would be basically precision at 7 because 7 is actually your ground truth. And these two metrics could be actually same if you end up predicting, okay, the same number of key phrases as the number of key phrases there are in the ground truth. And so what's the advantage of using this? If a model predicts many bad phrases, so it will have a poor F1 at M. But if a model, say suppose, is very conservative, so you're basically dealing with the generative approaches. So say suppose the model is very conservative and predicts very few good phrases. So then you end up having a very poor F1 and O. So this is also something little bit unique in the Keyphrase world, and this matrix is well explained in this paper by one of my colleagues, Rui Meng. And actually this slide is actually you know a copy paste of his email that he sent to me when I asked him, what exactly, because I had a lot of confusion about calculating this matrix while actually coding the library that I'll be talking about. So these are the common approaches then. There are like supervised approaches, there are unsupervised approaches. In supervised approaches, you have binary classification, sequence tagging, then sequence to sequence, and then unsupervised approaches, you have statistical and graph-based ranking. So let's quickly go through unsupervised approaches. As I said, there are two kind of unsupervised approaches, statistical and graph-based ranking. So but most of them have like these basic steps. So you start with, document processing, then you select a bunch of candidate phrases, and then you come up with some kind of algorithm which kind of ranks these candidates or scored these candidates, and then you do some kind of post-processing to actually identify these key phrases. And so now I'll tell this candidate selection phase, the step can be very interesting actually. And most of the innovation, to be very frank, kind of happens in the candidate selection and the candidate ranking or scoring steps. So in statistical methods, it's like, you use some of the common like statistical based features, like for example, TF-IDF scores and, co-occurrence based features, and then you try to rank the phrases. So there are a couple of, libraries out there which helps you to do so. And then, in graph-based ranking, your ultimate aim is to form this graph of, phrases from a single document. And how you do that, you identify basically textual units that best define the task at hand and add them as vertices in the graph. And then you identify the relationships that connect such text units and use these relations to draw edges between these vertices. And you can either weight the edges or you may not weigh the edges. And there are various techniques, exploring these different ways of weighing and weighing the edges. And then you iterate the graph-based ranking algorithm until it converges. For example, a very popular ranking algorithm is PageRank. And then you sort the vertices on their final scores. And there are several, graph-based approaches, and text rank was one of the first approach, which I really like, and it's still popular today. And Key to Wake is one of the approaches that I worked on, and this was published in NACL in 2018. And this is a very effective approach and very practical approach that interestingly worked very well for me in my work. And supervised approaches, the supervised frameworks can be, kind of categorized into three. One is a binary classification. You basically do a lot of feature extraction from different candidates that you have identified, and then you pass it through a binary classifier and say, ask the classifier whether this is a key phrase or not a key phrase. Then sequence tagging, which is which is gaining a lot of popularity these days, and I'm very interested in this particular method. And this is basically, a very similar kind of setup like NER. And then sequence to sequence, which is basically, you have an encoder decoder architectures are the most very popular these days. This is widely used in key phrase generation. Now in supervised binary classification, people have tried various kinds of methods. and they have basically have various ways to extract features, and some of them are statistical, positional, linguistic, contextual, and then sometimes also based on external knowledge bases like Wikipedia. And then they basically pass it through a binary classifier and try to categorize them into a key phrase or not a key phrase. Now, when it comes to key phrase extraction and sequence tagging, this is a paper we published in ACIR 2020, and the code and the data sets, all of them are available publicly. And this was a paper which actually used some of the modern contextual language models and actually posed the problem of key phrase extraction as a sequence tagging task, and showed that the modern language models are very powerful. So one of the reasons why sequence tagging is gaining popularity is because there are a lot of shortcomings of the previous approaches. One of the major shortcomings is in the candidate selection phase. In candidate selection phase, people come up with various kind of rules. Some people extract named entities, noun phrases, parts of speech tags. Some people come up with very interesting way to extract n-grams. And if you actually try to go and try to reproduce these rules and results, it's very hard to reproduce them. And it's not a unified process. Okay. But for example, if you throw in a long document, which often appears in real life, actually, so if you take each of these methods, and these are actually the average number of candidates which got generated by different kinds of rules, of each for rules developed by these methods. Now, I mean, there's a huge there's a lot of variation, and it's very much kind of manually driven, handcrafted rules, and it's totally dependent upon what domain you are basically, because some of them are very really suits well for scientific domain, but then some of them may not do so well in other domains. So now when it comes to sequence tagging, there's a lot of advantages. There's no heuristics and not much pre-processing, and not many rules. And it's a kind of an unified process. And it helps you to do like an optimal assignment of key phrases, because the the model itself learns like how many key phrases I need to actually extract, and leverages techniques of other sequence tagging tasks, and also captures a lot of long-term dependencies which the other tasks or other models cannot. So in sequence, treating key phrase as a sequence tagging, you simply take take these documents and tag the key phrases using any of the popular tagging schemes. For example, in this example, we have tagged it as BIO scheme, and you basically train a BiListium CRF model, okay, using any of these modern contextual embeddings, and you get awesome results. And so we tried out various embeddings and kind of explored them and kind of benchmarked some of these data sets, and we saw that Rubata, BERT, or the BERT family of models really really work well in identifying key phrases when you treat it when you take the token classification model for each of these language models. So we also looked at exploring GANs for key phrase generation. I know this is a work that got published in EMNLP 2020, and it's a very interesting read actually. So we actually didn't we were successful in the abstracted key phrases and generating very good high quality abstracted key phrases, but we didn't get any significant advantage over identifying extractive key phrases. And we kind of explain our failures in this paper as well, and the successes. So it's a good interesting read. And but then overall challenges that you see in this area is that in real life you often experience long documents. There are multiple topics covered in the documents. There are multilingual documents. Documents are coming from different sources. There's hardly any annotation guidelines. There are evaluation challenges, and there are multiple domains. So it's very hard to generalize. So these are more or less overall challenges, and I really encourage you guys to actually think about solving some of them. So now, given that we have the necessary background, let's dive into, learning rich representation of key phrases from text. I just would like to actually wait a little bit. Any like question that I can answer probably?
So I had a question. So, so I was glad you talked about the like unsupervised methods as well, because it seems like your focus has largely been on trying to come up with like a supervised way of doing it. But the challenge with that is the supervised methods are only as good as the keywords you've been given and
Right.
of the source you're training on, right? So if you're training on the abstract of like of a paper, right, and trying to come up with the keywords based on the abstract, well, like I have the abstract, that's already a pretty good summary of what's in the paper. I want the keywords to represent what's in the rest of the paper. And that may not be in your training set, right? So I guess my question is like, have you thought of doing any like, I mean, this seems like hard and expensive for like a Turker to do, but to like give someone a keyword and then have them look at the source material and then judge whether that the keywords gave them a good understanding of what was in the source, right?
Yeah.
Because that seems like that's what I would like to use keywords for, but that might not be how they're typically used, or am I making sense?
Yeah, absolutely. Actually, this is a very interesting thing that you have pointed out. So in my like practical experience, I think if you're in a industry setting, I think you will still go for unsupervised key phrase extraction methods. And then when you want to evaluate these key phrases, ideally what you would do is that you would actually extract these key phrases using some of the interesting unsupervised techniques, and then you would ask some humans to evaluate, okay, does this sound right? Okay, is this a key phrase that helps you to understand what's going on in this document? And this is the exact setup that we actually used when we were actually building a key phrase extractor in Bloomberg. And you're spot on actually, but the issues that I see is that with a lot of these unsupervised methods, they're not as good as the supervised methods. So when you have annotations, I think I would really encourage people to try out supervised methods, because I think they're really good and they understand the domains. And with this advent of these language models, which I'm going to talk about now, I think they have really, increased the performance of key phrase extraction and generation methods.
So, but when you say, they're not as good, they've increased the performance, but is this like basically, as quantified by doing a test train split and measuring on the objectives that they're designed to optimize? Or is this based on your personal experience in using them, like, oh, that actually did summarize these documents? Because if it's the first one, well, that's a function of using supervised methods. Of course they're going to do better, right? Because they're designed to optimize that.
Yep. Yeah, so actually both actually. So if you actually look at the literature today, if you look at these unsupervised methods, they often, you'll see they don't perform in this domain actually to as good as the supervised methods. So you have scientific articles, you use unsupervised extraction, use a supervised extraction, you will see that supervised model pretty much beats on the trend these validation splits. One of the key challenges which I see is that some of these unsupervised methods are very much rule based. They kind of heavily depends upon what the author has come up with this new strategy of selecting these candidates, and sometimes it's very hard to rank so many candidates, okay, and come up with the best candidates which represent the entire document. So I think there are challenges, a lot of challenges on supervised methods, and similarly there are a lot of challenges in supervised methods. There are pros and cons in both of them. Yeah.
Great, thank you.
Yeah. So so language models, as you guys know, assign probability values to sequences of words, and they're everywhere today. People are like getting news every day, of a new language model, and we are now at a stage where we are using it in production and deployment in machine learning teams. And BERT was one of such models which really revolutionized, and it kind of introduces the masked language modeling approach and performs like the state of the art in various tasks. And right from there, actually, I think there were several approaches that have been proposed. So I don't want to like bore you guys to talking about that. I assume that all of you are aware of these. So now, why language models? So this is like an excerpt from Sebastian Ruther's blog. And I mean, the remarkable success of the pre-trained language models is surprising. And one reason for the success of language modeling may be that it is a very difficult task, even for humans. And once you actually learn these masked language models, you end up actually learning about the syntax, semantics of the language. I mean, this might be a big claim, but this has been something that has been observed over time, and there's a long way to go, I do agree. But this is certainly a good approach to learn about the nuances of the language. So why not? I mean, this is a picture of my daughter who is holding a flashcard, okay, and it's basically a mass language modeling, because she is just filling up these characters of pool, okay, and this is immensely helpful for her to learn these words. And yeah, I see. I don't actually argue that. I'm really hopeful that machines are going to get benefited by that as well. So now pre-trained language models, on a huge corpus can learn universal language representations and help with several downstream NLP tasks. Pre-trained language models have also provides us with better model initialization, leading to better generalization performance and speeds of convergence on target tasks. Then pre-trained language models also can be regarded as regularization that helps in avoiding overfitting on small data sets. Now, why would we actually even think of building a key phrase language model? And so I think when we started this work, we were interested by some of these questions. Can we formulate a pre-training objective for language models that can learn better representation of key phrases? Does learning rich representation of key phrases in a language model lead to performance gains for the task of key phrase extraction and generation? I mean, that is something that is obvious. You would like to have that. And then do rich key phrase representations add other fundamental tasks in the LLP, such as NER, QA, RE, and which is relation extraction and summarization. So, and one of the things which we are still trying out is that language models tends to generalize really well across domains. So can we really do few shot learning and zero shot learning using some of these language models and train a rich language models which understand key phrases well in one domain, and then use that language model to actually generalize across multiple domains for identifying key phrases. So one of the like motivation was this Pegasus paper, which at this point I came to know that Google is using for, summarizing their documents in Google Docs. And it basically, builds on top of, this gap sentence prediction, and performs really well in the task of summarization. And it kind of, intrigued me a lot. Maybe we can do something very similar to for key phrases. And now when you actually look into key phrases, they're basically spans of text, and they're basically phrases which you would for which you would like to learn good representations. But then there are existing models like Spanbird, which already learn these representations very well, and they do pretty well in some of these span based tasks like NER, question answering. Now, but if you actually think carefully, as I said before, not all phrases are key phrases. So given a context, not all phrases can be tagged as key phrases. Okay, but Spanbird did show a way to us actually to learn rich representation of phrases. Now, there's another this task which basically learns very good span representations, which is the text infilling task, which is basically proposed in the BART paper. And these two basically ways of learning span representations really motivated us to actually come up with a new approach of learning representation of key phrases and tweaking some of the pre-training objectives of these language models. So that's what we're going to talk about now. This is what we came up, and this is like a pretty complex diagram. Let's go through it one by one. Okay, so basically, most of these modern language models apply masking strategies. So in order to learn, a rich language model representation, so you have input text, and this is like the popular paradigm of masked language modeling. So you have input text, you basically apply token masking, and you'd ask the language, you would ask the model to actually predict these masked tokens. And there are various ways to actually select these tokens. And then we do apply this token masking, and we build on top of Robata. And our KBIR model, takes and masks tokens very similar to Robata, and then tries to predict the token. Now, apart from token prediction, okay, we also do key phrase masking. And this is actually the interesting part, actually. So apart from masking tokens, what we do is that we also randomly select key phrases, which we also get from the corpus that we actually use for training. So we actually use the OAGKX corpus, which consists of like 23 million scientific abstracts, and they have like abstract and already author assigned key phrase pairs, and we use it to train a large language model. So we use the key phrases from there and randomly mask some of these key phrases. Now then, how to actually learn a representation of these key phrases then? So here we actually introduce this key phrase boundary infilling task. And basically what we, as you can see over here, in order to learn, or what we do is that the idea is that you mask these key phrases, okay, and then you have to actually identify these key phrases. So there's several ways to do so, actually. And we kind of got inspired by the text infilling task, which was proposed by BART, but then BART did it in a generative setting. How would you actually do it in an encoder setting? So that's what makes this approach really novel. So the idea is, now given this context, you have to predict the key phrase, which is X3 that you have masked. And what you do is that you take these representation of the boundary tokens, which is also something done in the Spanbird paper. And then you also take the position encodings, position embeddings. And then with this representation, actually you try to predict the key phrases. And now when you actually try to actually predict this, you don't know, like a key phrase could be like 2 words, 3 words, 4 words. It could be and you basically are so we not only like predict the key phrase, but also we try to predict the number of tokens that that key phrase might have. And this really helps. This provides a very strong signal in actually predicting the actual key phrase that has been masked. And we restrict our masking to only 10 tokens. So we do not predict any key phrase which is longer than 10 tokens. So now these are some of the details, which is very interesting. So we basically replace the entire span, in this case, a key phrase with a single mask token, which is something very similar to what text infilling task does in BART, but now we do it in an encoder setting. So we had to do some changes. So the idea is to predict the original tokens using the positional embeddings in conjunction with the boundary tokens. And a lot of you might be thinking, oh, how is it different from SpanBART? Like SpanBART also does this, but this is a more challenging task than SpanBART's objective of individual mask token predictions. So as the model must predict how many tokens corresponds to a span. So that's why we have this another head which actually tries to predict like how many tokens are there in the key phrase. And different from SpanBART, the SpanBART objective penalizes like incorrect predictions of a sequence of tokens. Does not penalize actually incorrect predictions of a sequence of tokens within a mask span. So it penalizes like token by token, but now we consider in the entire sequence of tokens. So we propose a cumulative loss across all the tokens in the mask span to capture the intra-span token relationships to learn better representations. So this is how we were able to actually implement the text infilling objective in a like encoder setting. Now, apart from that, the last thing that we did was the key phrase replacement objective, which is basically you randomly select the key phrase and then you replace this key phrase with another key phrase which comes from a fixed vocabulary of key phrases, and then you try to just classify you use a binary classifier and say, okay, whether this key phrase is replaced or not. And this is basically we're introducing contrastive learning, which really helps a lot in quickly learn as well as accurately learn these phrase representations. And ultimately we basically combine these losses and basically train this model in a multitask learning setup. So this is the KBIR objective. And there's another objective that we propose in the paper, which is basically a modification of the existing BART objective, which we call as KeyBART. So in this objective, as we all know in BART setup, it's basically a denoising auto encoder. There's a lot of noise that is introduced in the original text, and then the idea is to actually generate the original text from the noisy text. So over here in KeyBART setting, what we do is that we take the original text, we introduce the same kind of noise like token masking, key phrase masking, and key phrase replacement. And instead of actually trying to predict the original text or generate the original text, what we do is that we try to generate the key phrases that are related to the document. And this way we train another model on top of BART, and then there's another model that we train in order to be fair, because we kind of what in this in this model what we do is that instead of generating the key phrases, we actually generate the output text. So we do this so that we can do a fair comparison between these two setups on the same data set. So experimental setup, as I said, like we would use the OAG case corpus of 23 million scientific articles from various domains. Details could be found in the paper, and we get a pretty significant bump in scores in some of these data sets for keyphrase extraction, and pretty much beat the state-of-the-art models on several data sets. For keyphrase generation, also, we pretty much, beat some of the state-of-the-art models. One interesting observation is that we also, which is something that we want to explore in the very near future with these language models, is we also took keybart and actually didn't fine tune it, but directly tried to actually predict these key phrases, which is basically a zero sort setting. And we observed very interesting results. Actually, the results that we got for inspect corpus was the highest. So this is something that still interests us, and we still need to figure out why. But I think I think we still want to actually understand how these type of models, language models, which with a task specific objective, could be further used in zero shot and few shot learning of key phrases across different domains. And we got a very similar, results for absent key phrases, pretty much SOTA results. What is interesting is that we got very good results for other type of tasks also after learning this model, which is NER, relationship extraction, and also QA. And we also achieve, state-of-the-art results in summarization. And so I think details can be obtained from the paper. However, the models are readily available for you to download in Hugging Face, and you can simply, pip install their transformer library and just point to our models, and you can download them and play with them. The last bit of my presentation is DLKP, and I see that I'm out of time. So DLKP is a effort to actually, develop a new deep learning library for key phrase extraction and generation, which is completely missing. And there are several pain points that we actually went through while experimenting and developing various key phrase extraction and generation methods. So I think, that's the main aim, to actually fill up that gap and develop a new library, which kind of helps you to try out all these extraction and generation methods and readily access the benchmark data sets and evaluation metrics. So it's based on top of transformers, and training and evaluating a keyphrase extraction model is as easy as this. So you import the required modules, you initialize the data arguments, you actually point it to the data set which is in Hugging Face Hub. This gets downloaded in your local laptop. And then we have already pre-processed the data for you. And we have these documents and already biotagged data and for key phrase extraction. And we have all the data prepared for the key phrase generation as well, with a proper separation of extractive and abstractive key phrases. And then it's all about initializing the trading arguments, initializing the model arguments, which would automatically download the models from the Hugging Face Hub. And then you just simply train and evaluate. So, and yeah, once your model is trained, you can easily load the model and predict on a new piece of text. So I'm pretty excited about this library. So it's still a work in progress. Any volunteers, really appreciate, if I get any volunteers to. This is something that I work with another student of mine whose name is Amardeep. So we pretty much, work in our free time, on this library. I think it's high time now we recruit more volunteers to work more on this library. So I think there are various future directions to explore. And we do lack end-to-end methods for identifying key phrases from long documents. Domain adaptation and cross-domain key phrase identification is something that's very, very required even in the industry setting, especially like multimodal key phrase identification is something that is completely not looked at and by the research community. The how understanding how to train better language models. So I'm very excited about language models, because what I see is that these language models really bump up the performances, and I think there's much that could be obtained by exploring them more for these task of key phrase extraction and generation. And yeah, we need more data sets in different domains. We need to work on proper guidelines for annotating key phrases and evaluating them, and clearer definition and metrics for measuring keyness properties. And of course, like zero shot and few shot key phrase generation is something that the community should work on. So if you want to learn more about key phrases, so myself, Rui Meng from Salesforce Research, and then Florian from University of Nantes is presenting a half-day tutorial on Sunday, April 10th at the 44th European Conference on Information Retrieval. So feel free to attend that tutorial. And then I would also like to advertise about the work that my colleague, my ex-colleague, Mayank from Bloomberg is presenting on the impact of and the importance of key phrases in building NLP products. And I'm very excited about his presentations, because a lot of us often don't understand how key phrases are important in some of the products that we build. And I think this presentation is going to be very interesting for helping the audience to understand that. And lastly, I thought of actually talking about Moody's and the work that we do, but I think I'm pretty much out of time. But I want to just advertise about the opportunities that we have at Moody's Analytics. So there are multiple positions of machine learning engineers and machine learning scientists. We are a team which really encourages publications and external contributions. And we are very excited to grow this team. And obviously we are not there yet, as compared to some of the other mature teams in other companies, but we are growing really fast and we do some very, very exciting work. There are several products that we have impacted and has owned several awards. And so we work on various kinds of machine learning methods, like natural language processing is something which is very heavy at this point, and information retrieval. There's a lot of information extraction efforts going on. We have a very rich set of data, which is very unique to our company, and I don't think any other company actually has this kind of data on entities, especially people and organizations, and how they're connected with each other. So we're very interested to work on knowledge graphs and graph neural networks. And since we actually operate in the financial domain, I think explainable AI and explainability and interpretability of our models are a very important thing. So I think we're very interested to hire people who actually can work on explainable AI as well. So I think that's where I would like to end. So
thanks, Debanjan, for this wonderful talk. Maybe we can clap virtually, or and I think we can take one question, a quick question, if anyone have or want to ask one, or anyone. So yeah, so this library, what you are trying to build. Just a quick question, so information about kind of thing. So right now, like so you are looking for people to work on this to basically put out more tools and availability for easier deployments kind of thing, or more the one-way path kind of thing on the key phrase thing.
So we have basically built a basic framework. Okay. And at this point, we can easily train and predict using some of the transformer models, and it's very highly integrated on transformer models. What is missing at this point, I guess, is we need to build on top of this basic framework and would like to add more and more methods, so that anyone can come and this library can become a like a one-stop shop for key phrase extraction and generation. Because one pain point that I have faced while actually working in this area is that it's very hard to reproduce the results, which are often kind of reported in the papers. And then I think this is something common across the NLP domain. And there are often like libraries that you go and try to extract some code from here and there. These are like separate libraries, some shared by the authors, and which is not maintained over time, and they easily get old, and it's very hard to reproduce these baselines. And would like more volunteers to work on uh, some implementing some of these baselines. Also, there are a lot of exciting work being done on top of the transformer models. So language models, as we saw, has really proved to be a very useful for key phrase extraction and generation. And I see a lot of work being done in that domain, and it would be nice to actually replicate some of those work, and and implement some of those models in this library. So yeah, those are some of the things that are typically in my mind. Yeah.
Okay. This was very informative talk. I thank everyone for attending it, and especially thank Debanjan for presenting and making us much more aware of key phrases and uses and why it's important. I hope. Thank you all. Thank Debanjan once more.
Thank you so much, Vivek. You all have a good evening.
Thank you all. Bye.
Bye.